All right, good morning, good afternoon, everyone, depending on where you're dialing in from. My name is Caitlin Harbeck. I'm an Associate Program Manager for Cryospheric Sciences at NASA headquarters, and I am the co-lead for the IARPC Glacier and Sea Level Community of Practice, along with Zoe Corville. We also have Glacier and Sea Level Community of Practice leadership alum joining us today as well. Joe McGregor is here in the audience. Thanks for joining us, Joe. So if this is your first IARPC Community of Practice meeting, welcome. If you're not familiar with IARPC, it's the Interagency Arctic Research Policy Committee. Brings together all different federal agencies, Arctic researchers, communities, and more beyond that. To share their work and to team up to improve research operations in the Arctic. So as you might imagine, this community of practice specifically is involved or is focused on research improving understanding of glaciers and ice caps in the Arctic, specifically the Greenland ice sheet, in order to help resolve forcings and impacts for mass balance changes, and specifically how those changes in the Greenland ice sheet and other Arctic ice caps impact sea level rise. So we often have a lot of talks about glaciers, so it's always fantastic to be able to have a little bit of sea level rise discussion in our meetings. So I'm not sure how many of you were at the annual meeting of the American Geophysical Union in December, but Dennis and the rest of the Earth Information System team gave a fantastic town hall on the last day of the meeting, and so I was excited to have them and invite them to give us a briefing of the Sea Level Rise and Coastal Resilience Project that they are working on. So I'm sure that Dennis will jump into an overview, but the Earth Information System, or EIS, is designed to monitor and to assess humans' impact on climate change and other systems in the natural world. So EIS is responsible for providing a framework that integrates data from NASA satellite missions, different modeling platforms, and research programs to help us better understand processes going on our planet, whether it's sea level rise, wildfires, other there's a handful of them. I can't even remember all of them now. Terrestrial hydrology, terrestrial ecology, just to name a couple. So I'm going to hand it over to Dennis now to kick it off and give us a little bit of background about EIS, and then to talk specifically more about the sea level rise program as part of EIS. So Dennis, take it away. And I think Ian, you are sharing your slides, right?
Thank you, Caitlin. Go ahead and share, Ian. Yeah, thank you to the entire IARPC crew here for inviting us and for giving us a chance to present our work to you all. So the way we have it structured is we have kind of, I think we have a talk that'll maybe last half of the meeting, and we're hoping to be able to do some Q&A after that. I told all the IARPC folks the flu is running rampant through my house right now, so I'm personally okay for now, but the rest of the family is sick. So I'm going to do an intro and overview, and then unfortunately I'm going to have to jump off. But I will leave you all in the very capable hands of Ian Fenty and Augusto Getterana, who will be able to answer questions and talk more with you all about the project. So we're here to give you a bit of an overview and of this Earth Information System EIS project that we've been working on at NASA for a couple of years now. And if you'd like, I'll go ahead and invite you, excuse me, to scan the QR code or go to that URL down at the lower left. As I'm talking and presenting slides, you can browse our website and kind of learn more in the background. And we've got the QR code at the very end too. So that website is the best starting point to learn more about EIS and to connect with us. Okay, next slide, please, Ian.
It's very sensitive there.
Seems to be jumping. There we go. Okay, that's perfect.
Okay.
Looks good. Okay, so why did this project get started? What was the purpose of it? The motivation, and this is not going to be news to anyone on this call here today, is that the need for synthesized higher level information about the Earth system that's relevant for decision making is increasing, and it will continue to increase over the next who knows how long. More and more stakeholders of this information need timely and well-tested information about the Earth system to make decisions. NASA, we think, is uniquely positioned to provide this kind of information because we provide the underlying satellite observations and invest in models that use those satellite observations. And so the idea behind this project is to provide that highest level information about the Earth system that can be used in decision-making environments. So this kind of information is needed from, at all kinds of spatial scales and by different types of users. So going from global to more local scales, you can think about the assessment reports that IPCC writes, or the WMO, for example, or the National Climate Assessment. That kind of synthesized information makes its way into those reports to get disseminated. But it also then ultimately gets used at more regional and local levels where the rubber really meets the road and decisions need to be made based on that information. So, at NASA, I would argue that we have made inroads and invested in developing partnerships and relationships with stakeholders around certain thematic areas or within certain science disciplines, but these tend to be kind of siloed. So we have projects that serve the needs of certain kinds of stakeholders, but we don't have anything that really connects across the board. Next slide, please. So the Earth Information System was started as a pilot project 2 years ago to see where we can connect the dots across all of the different thematic areas and stakeholders that we're trying to serve. And by doing that, we're hoping to accelerate the creation and delivery of actionable science-based information. So these are the focus areas that we have stood up so far, or are focusing on within the Earth Information System project. We have water security, fire, agriculture and crops, greenhouse gases, and sea level change and coastal risk. So I'll give kind of an overview of the whole project, but we're really going to focus on some examples of some really cool work that we've done in the sea level change and coastal risk thematic area. So the strength that we're bringing to the table is that we're really trying to work across these different traditionally siloed or disconnected thematic areas and put together a foundational set of global data products and tools around those data products that will make it easier, so accelerate the creation of information and, again, the delivery to those end stakeholders who need the information. Go ahead to the next slide, please. Not only are we trying to connect across science disciplines, but within NASA programs, we're also trying to build bridges across these different NASA programs. So the way that we've approached this is within EIS, we have a transdisciplinary team that brings together expertise from cyber infrastructure and data systems, physical science researchers, applied science researchers, and ultimately bringing everybody with these diverse sets of skills all onto one project within one team. And that's how we feel we can deliver on our mission. Next slide, please. So the way we work, this is kind of more of getting into the how we work, is the foundational layer that we are all building, that all these thematic areas are building upon, is a set of interoperable cyber infrastructure tools, analyses, and data sets that we are all working on creating and then building our scientific understanding on top of that. So we are trying to work very much in the cloud and utilizing new and emerging cloud technologies and platforms like the Veda platform that that NASA is investing in, as well as the MAP platform and SMCE. I won't go into the details of these very much, although I think we do have some more information about it in the examples that Augusto and Ian will show. But suffice it to say that these are new cloud platforms to do research and analysis, and also delivery of tools and data products. And we're all trying to work across the board, across these thematic areas, all together on these platforms to leverage what we're all doing together, so we're not duplicating each other's work, and also learn how to do, you know, kind of next generation analyses on emerging cloud platforms. Next slide. On top of the interoperable kind of tech and data layer, this is how we are enabling cross-disciplinary work. So because we're all kind of learning how to speak the same technological language and drawing on similar data sets, that's what enables us to do multidisciplinary work better. So this is an example. This just has a few examples of some cross-cutting interdisciplinary science work that we're working on. We have more examples of these. I won't go into the details, but you'll hear more from Augusto on that top center one about how we're linking coastal and inland flooding in a modeling framework. Next slide. So as I've said, you know, not only are we putting the pieces together, but the way we're delivering can also be, we're also trying to sort of push the bounds on in delivering information in different ways. So we are, of course, writing, you know, doing the traditional thing of writing peer-reviewed science papers, but we're also learning and prototyping new ways of delivering open source data and analysis workflows, typically through Jupyter notebooks, but also other means. The Veda platform, one thing that it really excels at is delivery of interactive web stories. So if you've ever worked with or have seen a story map from Esri, these are very similar. And on the very right, we're also in some thematic areas, like this is an example from the fire team, we're actually working very closely with stakeholders and users to deliver data products in such a way that enables them to plug them directly into existing workflows. So we kind of, we have examples of different cases across the different thematic areas, but we're trying to find new ways of delivering, not only putting together the data, this information, but delivering it as well. Next slide. So yeah, and the next slide is the top of this pyramid, and this is the whole goal, the mission, not just of NASA, the NASA Earth Information System, but also NASA's new push to do science to Earth action, and that's to enable science-based decision-making that is driven by these data products that we're putting out. So if you go to the next slide, this will be my last slide, and then I'll go ahead and turn it over to you, Ian. So today what you'll see is a few examples from the sea level change and coastal risk thematic area. Ian will show you some really cool utilities that enable users to run the ECHO model, the ocean reanalysis, in the cloud. And I think really lowers the barrier to running that and doing actual analysis. Ian will also show you a dashboard, cloud native dashboard that we've put together that is open source and enables researchers to very easily and quickly play with SWOT data from the recently launched SWOT satellite. And then finally, Augusto will round us out, and he'll show you that work that I alluded to, where we're disentangling the drivers of coastal flooding, specifically focusing on Bangladesh. So I'll go ahead and turn it over to you, Ian, and I'll step away. But again, thank you all for your time, and chat soon.
Good luck today, Dennis. Okay, that was a fantastic introduction by Dennis. My name is Ian Fenty, and I'm a research scientist at the Jet Propulsion Laboratory. I've been working on this, involved in EIS for about 2 years, and it's been just personally a really great experience because it's encouraged a lot of interaction between disciplines that I think don't normally have the opportunity to work together on a project. And one of the ways that just like the low level way that we're interacting is with common cloud-based compute platforms. So we all hear about analysis, big data analysis being done in the cloud and how the cloud is the future. For me, I was very skeptical. I'm more of a problem-driven technology adopter. Historically, we haven't needed the cloud. Cloud didn't exist, we didn't need the cloud. But there are lots of examples of data sets these days that are so big that working in our traditional ways on our local computers or local university clusters or even on our massive supercomputers, they all break down. And one thing that really hit me was with one of the large-scale global ocean simulations that we make with Echo. This data set, the output of the data set is measured in petabytes. So it is just literally impossible for people to download these data sets. And yet the data set is, when it was generated, people recognized that it would be extremely useful for some basic investigations of ocean dynamics. And specifically, this data set became available a few years ago during the development, concept, and construction of the SWOT altimeter. So during that time, a bunch of folks got together and they tried to figure out how to connect to that data set from the cloud so that people who didn't have access to the NASA supercomputer, but did have access to commercial cloud resources, could interact with this data, do calculations on the cloud, and to complete analyses that would otherwise take literally months of computer time in a matter of hours. So that sort of at that point, I became a true believer in a sense of the potential for EIS and the kind of cloud-based paradigm that it was promoting to help all of us do like the next level science. So I was originally going to talk about these the points 1 and 2 you see on the screen. The first one has to do with accessing the model output, doing computations in the cloud, and even running our global ocean model in the cloud. And that's cool, and we can talk about that another time, but I decided that probably the more cool and like immediate example of interest to this community would be the second point, because it is very timely in that it relates to the SWOT satellite data. And the SWOT satellite data, if you're involved in this community at all, has just very recently become publicly available. Publicly available doesn't mean that it's usable. And I'll talk about that. I'll talk about that now. So I'm going to stop sharing this PowerPoint, and I'm going to start sharing. I'm going to start sharing, excuse me, I'll stop sharing this PDF and start sharing my PowerPoint. Okay, can someone please tell me whether they see this slide, a new slide?
Yep, the SWOT level 2 sea surface height cloud. Yep. Okay,
so this tool I'm going to present to you was developed by our EIS JPL colleague, Jimbo Wong, and some interns over the last summer, of course. And Jimbo has been working on SWOT for more than 5 years. And so, as a scientist, oceanographer for 5 years, he's, stared up at the sky at night and said to himself, how can I possibly analyze these data when they become available, because the data sets are just going to be too big. So he kind of took it upon himself to tackle this problem. So just very, very briefly, the SWOT altimeter is NASA's first global survey of Earth's surface water. So it's surface water ocean topography. I'm an oceanographer by training, so the ocean topography part is the part that motivates me the most. I can think about what to do with it most easily, but a lot of Arctic work has to do with hydrology, and so many of you are probably familiar with potential of SWOT to advance your science. SWOT also very obviously has some potential for use on ice research, sea ice and glaciers, although those two topics didn't seem to be as highly promoted on the liquid water part of this mission. But what I've seen of SWOT on sea ice and on glaciers is like astonishingly cool. So I think this will be an area where SWOT is used, will be used way beyond the original science requirements. So look at the third point. The third point is that SWOT will generate 20 terabytes of data per day. And my machine at home that I work on has a few terabytes of data. And of course, we care about changes of the cryosphere and the ocean system. So analyzing and downloading these data are totally impossible. So let's put some hard numbers on it. These bar charts on the right are some benchmarks. I think look at the first three benchmarks. Basically for reading and remapping, doing some calculation on one of these files on a state-of-the-art machine, excuse me, a file that is about the same size as a SWOT file, is about 40 seconds per file. And SWOT will have, on the order of 20,000 of these files. So totally impossible. And so we can see a potential for the cloud to speed this up. But the question is, for me, and probably for many of you, how the heck do we do that? Just because someone throws the word cloud around doesn't mean we know how this is going to actually help us in practice. So Jimbo, he has this really nice role sitting between the SWOT mission and the NASA's physical oceanography data center, the PODAC. And the NASA PODAC, just like the NASA ICE, NSIDC, are both part of the NASA confederation of hosting and distributing data. And recently, NASA, the DACs transitioned, or at least plan to transition, all of their data sets into what NASA calls Earth Data Cloud. And if any of you use NASA satellite data over the last few years, you've probably been confronted with this thing, NASA Earth Data. But the idea is the data will be all hosted in the cloud so that NASA doesn't have to own and maintain all of the hard drives. And if the data is in the cloud, then users can do their analyses in the cloud without having to transfer the files to their local machines. And that's like the big picture idea of it. What Jimbo and his intern did was take this simulated SWOT data. He developed this before the SWOT data was officially released, to create synthetic SWOT data, put it in the cloud, and then learn the technology, the clever new tools to basically slice and dice that data in a way that makes it possible to do the analyses on like normal timescales. So this slide, these slides will all part of the record. I'm going to leave it on the screen, but I'm not going to speak through it, except to mention that, we are all probably familiar with this data set called data format called NetCDF. And NetCDFs are very super convenient, especially compared to what data sets look like when I first started doing science, because they're self-describing with metadata. But that turns out that that data format isn't optimal for cloud-based analyses. And part of what Jimbo and his intern did was do a deep investigation into what is, in this case, for SWOT at least, what is the most efficient format that's available. And they settled on this format called ZAR with this extra layer called kerchunk. And the kerchunk is basically the map that tells your cloud-based system where the data are hosted on the cloud. So data is on the cloud, and it's stored in the ZAR format, and you have the right map. Then accessing the parts of the data that you want becomes lightning fast compared to the alternative. So after they did this analysis, they made this prototype interactive Jupyter Notebook dashboard. It's folly to do a live demo and on talk, so I didn't do it. We just have the screenshot. But what the screenshot allows you to do is move through the different tracks, the orbital tracks, the different passes of the overpasses, and to zoom into areas of interest, and then to quickly from that area of interest, then subset out whatever variables you want. So this is a nice pass because it shows how far north the SWOT data goes, which is just about 78 degrees. From this dashboard, from the Jupyter Notebook, we can very quickly ask the tool to pull all of the tracks for a certain time period, and to do whatever calculations we want: means, medians, and histograms, PDFs, and to quickly plot these. So Jimbo gave me an estimate that making this one plot in the traditional way would take something like a week to download and to do the computation. But on the cloud-based system, it took 24 seconds. So that's the kind of speed up that we can expect to enjoy when we use the cloud to do analyses on big data like SWOT. I leave this up here. The notebooks that they developed are available on the PODAC GitHub, including this this second tool, which is how they learn to make the map. Recall that I said you need the data in the right format, and you need the map where the data is stored. And that's the second notebook. So the notebook that they developed, this interactive notebook example, it works fine. Right now, it still uses the synthetic SWOT data. The SWOT data is coming in. It is being processed and hosted on the NASA DAX. The conversion into the cloud optimized format and the creation of those maps is ongoing. So as soon as that pipeline is operating at full swing, then all of us will be able to pull out and analyze SWOT data with a very low latency. I think I've heard 2 weeks. Expect 2 weeks for a first look. So that's the current status of the notebook and of this tool. It's here. You can find it here on this GitHub, and with these few steps, you can spin it up in your own environment. And I had just a few more points to make about this. I'm going to stop sharing my screen, that I think are just, I think it was kind of cool. This, in this new era of this new kind of paradigm of open science, EIS is really promoting this within our communities. And I just think this is a great example of the FAIR practices. And I want to explain for a minute why. This all of the SWOT data is easy to find. It's all on the NASA Earth data. That's findable. In terms of accessible, the notebook, all of these notebooks are available on GitHub, open, transparent, distributable code. Everyone can access the SWOT data if you have a NASA Earth data account, which takes 5 minutes to make. The notebook can be, in terms of interoperability, the notebook can be run on all kinds of different machines. It has, interpretable is the SWOT data is like self-describing with metadata. The source code of the notebook is all right there in front of you. And the code, this is a good example of well-documented code. And finally, in terms of reproducibility, I can verify that this is reproducible code because I reproduced it. You know, I went over to Jimbo's office. I said, I've got 15 minutes. Can you show me this fancy tool that I hear so much about? And he said, yeah, let's do it. And I logged into my cloud compute account. I cloned the GitHub environment. I installed 4 packages and it worked just out of the box. We did it together. It took 15 minutes and I was able to rerun all the cells. In fact, I even modified cells just to verify that, this wasn't just a one-off. So, so I think it's pretty exciting. And I hope that not knowing about this kind of tool, knowing that this kind of work exists and knowing the potential for the cloud is helpful for your guys's work. Okay, that's all I have about that. And what I suggest is that I move to Augusto, and then after Augusto, we do questions. So I'm going to share my screen.
Hey, Ian, while you transition, Tim Bartholomew wants to know if you can provide links to those notebooks.
Yeah, I will provide the links in the chat when after in the question and answer part. Okay.
Sure.
Okay. Because I can't do it while I'm also doing screen sharing. Okay, let me go to full screen and Augusto.
Yeah.
This looks right.
Yeah, that's perfect.
Okay, go ahead.
Well, thanks, Ian. All right. So my name is Augusto Guetirana, and I'm a research scientist at the Hydrological Science Lab at NASA Goddard Space Flight Center. So I'm a hydrologist. I'm not an oceanographer. And that said, my focus here is on coastal flooding, and ocean is usually used as a boundary condition in my work, in the modeling work that I develop. I mean, it's good and bad. I think it's good here because it probably gives you guys a different perspective of how the ocean can impact hydrology from a land perspective. So in EIS, I co-lead the sea level change and coastal risk thematic area with Ian and Dennis, and I'm also part of multiple activities in the water security thematic area, and also the crop and agriculture. So I take advantage of these roles within EIS to lead some transdisciplinary work connecting hydrology, sea level change, and human activities. And today I'll talk about these issues in the Bay of Bengal, more specifically in Bangladesh. But why Bangladesh in particular? Because the region has been under extreme increasing climate and human pressure, with intensive groundwater pumping for irrigation, as well as sea level rise and decreasing precipitation. So there's a lot going on in that tiny region in the world. Bangladesh is currently the 3rd largest rice producer in the world, only after China and India, as you can see in the figure on the left. This is a result of intensive irrigation during dry seasons, in addition to the traditional wet season flood irrigation that's been over decades in the region. And that dry season irrigation has resulted in a loss of almost 3 billion gallons of groundwater in the past decades. I know that's not really sea level related, but we'll get there. So considering all these issues, we started engaging with local authorities, and that engagement has given us access, like free access, to a massive amount of data, which otherwise have restrict access. So we've been using that data in different ways, and one of them is to reproduce the groundwater dynamic over the past several decades. One of our findings is that for a certain period of time, groundwater pumping during the dry season increases recharge during the wet season. This makes the aquifers to act like a sponge. So this means that you have more groundwater pumping during the dry season. So it increases you make an additional empty space in the aquifers, and then during the wet season there'll be more infiltration. So all right, so but this sponge behavior can I'm calling that there could be other side effects, which I'm calling here cascading effect hypothesis. That means that so with more infiltration during the wet season, we have less runoff drops, and less runoff results in lower flood risk on the coast, which is good. But also less runoff means less surface fresh water, which could result in even more groundwater demand now that you have less water available on the surface. And it could also mean that more saltwater intrusion, since there is less fresh water to push the ocean water away, particularly with sea level rise. So basically here we're trying to link groundwater fed irrigation with sea level rise in their synergy on the coasts. So next slide, please. So we combine in situ data and satellite data with our NASA models to create multiple what-if scenarios in a way that we could isolate impacts of different factors that we assume relevant for coastal flooding in the region. So we first look at the impacts of irrigation on the water cycle. So for example, on the left side, we quantified for the first time the spatial temporal groundwater demand for irrigation and its impacts on water resources over the region. So as a result of these simulations on the right side, we are able to reproduce the groundwater depletion driven by intensive pumping. That depletion is observed through both in situ measurements and satellite data. I'm not showing here. You have to trust me for now. And finally, we also detected a substantial drop in runoff across the region in the bottom right, confirm our first hypothesis that intensive groundwater pumping results in runoff drop. So next slide, please. So we analyzed the impacts of 5 factors on coastal flooding. They are vertical in motion, natural sea level change, sea level rise, polders, they're also called levees, and the intensive irrigation that I just showed. So sea level data here comes from radar altimeters, and vertical in motion is this global gridded data set based on GPS observations. So storm surge is also a relevant factors contributing to coastal flooding, but it was neglected here because of lack of data at the time this work was developed. But I mean, it is an important factor. So socioeconomic impacts were quantified in terms of flooded population and cropland using the 2 maps on the left. And so the plots on the right summarize our main results. We can see that vertical in motion, natural sea level change, and sea level rise combined put about 800,000 people and around 190 square kilometers of cropland under flood risk. Vertical in motion impact alone is minor, is about like 8%. Polders, on the other hand, protect several times more people and cropland during annual events than the median event, justifying its use. So like it has like a higher impact in more extreme events. So finally, we can notice that irrigation decreases flooded areas, reducing populations and croplands exposed to flooding. And that confirms our second hypothesis. so that's an ongoing work. I mean, right now we're finishing some new simulations that we changed some parameters in the model to improve the flooded areas. So next slide, please. So in terms of Earth science action, that that was one of the points that Dennis presented. We've been very busy. On the left, there's a list of local agencies that we've been working with, and that work has been granted us access to unique data, as I mentioned before. There's also some pictures here of our team member Nishan Biswas. He's Bangladeshi originally, working at NASA Goddard. And here in these pictures, he's interacting with some stakeholders during a conference on flood risk in Dhaka last year. We also published a notepad in the Daily Star. The Daily Star is this leading English newspaper in Bangladesh. That op-ed was led by Nishan. And this engagement with local stakeholders resulted in a multi-institutional nature commentary published in 2022. That's in the bottom right. And that paper depicts the dramatic situation of water resources in Bangladesh. That includes the effects of sea level rise. So in the next slide, please. Yeah, so that's the last slide of our presentation. If you want to learn more about EIS, you can ask us, or you can also scan the QR code on the right. There's also the website where you can find some applications. And that's it. So I'd like to turn it over to Tony, or I think that she's presenting, right? Or Jan. I don't know who's speaking next.
Well, that's the end of our EIS part, Augusta.
Yeah.
All right, thanks so much, Ian and Augusto. So I'm just going to loop back to Tim's question in the chat about getting the links to these notebooks.
Yeah, I'm going to put it in the chat right now.
And if other folks have questions, feel free to drop them in the chat or just speak up. I guess I have a quick question. So Augusto, the project you presented was fairly specific. Are there plans within the EIS sort of ecosystem to add additional projects to the sea level rise and coastal resilience portfolio, or is this sort of it for now in terms of it being a test bed?
Yeah, so it's been evolving idea. So during the pilot, we did something similar for the Louisiana coast, like focusing on the Mississippi Delta. Our first work that was published sometime last year, and then this is a second step that it's been taking more time because a lot of data to be processed. But the next step is to apply the methodology that has been developed and polished over all U.S. coast and then global scale. So that's the order of things how you're working. So the target here is global scale, looking at all the global coasts. Yeah, and I'd like to highlight what Dennis mentioned before about the transdisciplinary emphasis that we've been giving to EIS work. For example, here in the work that I presented, we're combining sea level rise and coastal risk with irrigation and water security, right? So the other works developed combining water security and fire and so on. So we're trying to get this not I would say obvious thematic areas and try to find where they overlap, where they want to impact each other.
Great, thanks. Julie.
Yeah, two questions. I may have missed it. You have the impact of the irrigation there in Bangladesh. Did you also look at the retreat of the coastline along with that? Were you mapping that, or is that another thing that you could do with these data? That's my first question.
Okay, one by one. Okay, so that sounds good. So yeah, so the maps that I showed, I mean the model output will give you the flooded area. If that area becomes a permanently flooded area, you can assume that is a coastal retreat, right?
Okay.
But that's how it's a hydrological model, like a hydrodynamic model. So there's its limitations, but that's how we can reproduce the coastal retreat.
Okay.
But no, we don't the model cannot, for example, represent sedimentation. So the land is static.
I see. So my other question, and this is all fascinating, it's well beyond anything that I do myself, but I'm working in an area of Alaska, Southwest Alaska, that other people have called, not me, other people have called it Alaska's Bangladesh. Okay. Mm-hmm. And the problem there is very similar kinds of deltaic environment, but you've got permafrost. Is there a way to combine what you're doing in an area like in the Arctic, where there may be similar concerns about, water security, but they're not irrigating, right? But you have permafrost. Just wondering, is that something that you've thought about for dealing with in the crust?
Yeah, that's a good question. I don't usually work on freezing areas, so permafrost is not something that I always that I ever consider in the hydrodynamic model. But it's definitely something that we'll face, an issue that we'll face once we get to the global application. Yeah, and I started some collaborations with people at NASA GIS in New York, and they have a more physically complete routing scheme. I mean, it's simpler in terms of hydrodynamics, but they account for temperature and like freezing water. So I think with this collaboration, we will be able to include more frozen waters in the model. But yeah, that's a good point, and but I don't have a solution for that yet.
Okay, well, just thinking down the road, because there's I don't know, 30 or 40 villages that are in trouble.
Yeah, that's a good point. Oh, thanks.
Yeah, I know.
Right?
Yeah, Julie, I know that the EIS is definitely still a work in progress, and there are definitely still a lot of model parameters that have and data sets that have yet to be included in this.
Well,
so
put that one out there. Maybe 10 years from now, you'll have an answer, but I just think that would be a really great application in the high latitudes.
I thought that was a second question.
Nope, that was it, actually.
Okay. Good.
Any other questions, comments out there?
There are questions in the. I don't know if you're supposed to answer.
No, I think that was just Ian posting the PODAC.
Okay.
Whoops. Okay. And I see that Tim has turned his camera on, which generally means he has a question.
True. Thanks, Caitlin. Thanks, Ian. Yeah, so I was wondering about, it looks like you've shared a couple of examples of sort of accessing different NASA Earth data in the cloud through an EIS lens. Is your vision ultimately that the EIS will be some kind of like broader wrapper or entry point into kind of all NASA Earth data? Or is it going to be kind of a compartmentalized, some kind of notebooks and tools to kind of do specific tasks? What's the kind of like the end result?
I think it's the vision is very much work in progress, but I am fond of the term federation. So I think it's a what I imagine are these different federated groups, different groups that can whose data is interoperable, and through the thing that connects them is not the US highway system. It's that all the data is stored in the cloud, and that from any one cloud-based compute site node, you can access and work on these different data sets, and hopefully how you work is in an open science way that your analyses, your routines for accessing, doing the calculations, storing it, making all the analysis for your paper, all of that is transparent and shared with other people. So that's what's going to accelerate our community science.
Cool. Thanks, Ian. Thanks, Augusto.
There's a question in the chat. Was the reason for ZAR file size and chunk for speed, or was there a compression file size component that makes it easier to use in the cloud? I don't know about the compression file size component necessarily. Okay, I'll try to do my best to explain it very briefly, but it's 1 o'clock and I want to respect everyone's time. A long track level 2 satellite data is unstructured in that orbits can move a little bit. The individual data, the pixels aren't always necessarily located in the same place. So any one pass can comprise hundreds and thousands or millions of points. So if you only care about the coast in Southwest Alaska or near Bangladesh, you don't want to have to deal with the hundreds of thousands or millions of points along the swath. You want to be able to get just the part out that you need. And so ZAR and chunk is a way to store the data so that it knows about where, the individual points know about where they are in time and space. And the map is what tells you how to get to the pieces that in time and place that you want. So the reason for ZAR and chunk is in that sense for speed. Hope that answers your question. Are there any publicly available examples, information involving SWAT over ice? I don't know I haven't been following all the press releases, but I know there is a SWAT deck somewhere produced by our French colleagues that has examples over ice, slide deck. And if you want to see it, if it is publicly available, then write Jimbo, whose email address I'm putting in the chat. Okay, I'm sorry, I have to go. Thank you, everybody.
Thanks, Ian. Yeah, we're just past the top of the hour. Thanks everybody for sticking around. Thanks Ian and Augusto for presenting today. And watch this space. We'll have another IARPC Glaciers and Sea Level Community Practice meeting coming to you in early February.
Thanks, guys.
Thank you. Bye.